Hello, in this video we'll be learning about the Floyd Warshall algorithm to find the shortest distances between any two pairs of nodes in a graph. So the agenda for the video is I'll be introducing the topic followed by a brief history, and then I'll be explaining the algorithm, and lastly we'll solve an example using the same algorithm. Why is Floyd Warshall algorithm important? In general, the shortest distances between two nodes is a fundamental measure of connectivity and efficiency in a graph. Now, this provides an insight and solutions for a wide range of problems and applications. Overall, the shortest path algorithm is a fundamental tool in graph theory and has numerous applications in various fields such as network routing, transportation planning, social network analysis, and many others, making this an important topic of study in computer science and related disciplines. In transportation planning, finding the shortest distance between two locations can help to optimize routing problems, and optimizing the routing problem reduces travel time, which in turn helps minimizing the fuel consumption, and which obviously has a positive impact on the environment. This information can also be used to improve traffic flow and reduce the traffic congestion, as well as to plan more sustainable and efficient transport systems. Robert Floyd's paper, Algorithm of the Shortest Path, was published in the Communications of the ACM in 1962. The algorithm that he described used a matrix representation of a graph, which computed the shortest path between all the pairs of vertices. Now, the basic idea he used here was to start with a matrix that represents the graph and then use programming to iteratively update the matrix until it contains the shortest path distances between all the pairs of vertices. Now, during the same era, Stephen Warshall also published a paper titled a Theorem on Boolean Matrices. Now, in this paper, he presented an algorithm for computing the transitive closure of a graph using a similar approach to Floyd's algorithm. Now, the transitive closure of a graph is a matrix that represents the reachability between any pairs of vertices in the graph. Now, in both these papers, it was later realized that the algorithms were essentially the same, and hence the algorithm that we now know of is that's why I refer to as the Floyd Warshall algorithm. Here's how the Floyd Warshall algorithm works in more detail. First, we create a table that stores the distances between all the pairs of vertices in the graph. Initially, the table contains the edge weight between each pairs of adjacent vertices and is filled with infinity for all other pairs of vertices. Now, what this means is, if two vertices u and v are connected by an edge with edge weight x, then the corresponding value in the table for the respective vertices u and v will be x. If the two vertices u and v are not adjacent by a single vertex, then the value assigned to it will be infinity. Second, we start iterating over all possible intermediate vertices in the graph. In other words, we consider each vertex as a potential pivot that we use to potentially reduce the shortest path between two other vertices. Third, for each pivot vertex, we update the distances in the table based on whether or not using the pivot vertex results in a shorter path. Specifically, we compare the distances between two vertices without using the pivot vertex to the distances between the vertices using the pivot vertex. Now, if the later distance is shorter, that is, without using the pivot vertex, the distance is shorter, we update the table with the new shorter distance. We continue iterating over all possible pivot vertices until we have considered every possible intermediate vertex. At this point, the table will contain the shortest distances between all possible pairs of vertices. One important thing to note is that the Floyd-Warshall algorithm works for both directed and undirected graphs, and it can handle the negative edge weights as well. It has a time complexity of big O notation of n to the power 3, where n is the number of vertices in the graph, which makes it a relatively efficient algorithm for a smaller or a mid-sized graph. So the example that we will be working with is this directed graph G bar with 4 vertices and these edge weights. So we start this problem by constructing the first matrix A0 which will be n cross n, and hence this directed graph is on 4 vertices. We get 4 cross 4 matrix A naught. So the diagonal elements will always be 0, since starting from, let's say, this 2 comma 2, if we start from the vertex 2, we do not require to travel any edge to reach back to 2. That's why all the diagonal elements will be 0. Now 1 to 2. 1 to 2, there is no directed edge. This edge is from 2 to 1. So 2 to 1, there is 4. But 1 to 2, there is no directed edge. Hence, we assign it infinity. 1 to 3, there is an directed edge with edge weight 2. Therefore, we write 2 here. 1 to 4, there is no directed edge. That's why infinity. And this is how we create the first matrix A naught. Now, from this matrix A naught, we create one more matrix A1, where the intermediate vertex will be 1. Therefore, the first row and first column will remain fixed. This first row and first column will not be changed. And this diagonal elements will also be 0. Now, what we do is, we travel 1 to, let's say, we have to fill up this box. So, traveling from 2 to 3, 2 to 3, via 1, because 1 is our intermediate vertex, we travel 2 to 3 via 1, which is 2 to 4, 2 to 1, which is 4, and 1 to 3, which is 2. 4 plus 2 is 6. But 3, in the previous matrix A naught, we have 3. 2 to 3, there is a direct edge, 2 to 3 with edge weight 3, which is lesser than 6. Therefore, we assign it 3. Continuing in this manner, keeping the intermediate vertex fixed as 1, we travel all other vertices. We travel between every pair of the vertices, and we get this matrix A1. Similarly, continuing in the same manner, we get A2, where in this matrix A2, we keep the intermediate vertex as 2, and the second row and second column will be fixed, and between every other pair of vertices, the traversing will be done via 2. So if we are traversing from 1 to 4, we consider the previous matrix also. 1 to 4 will be traversed via 2, which is 1 to 4. 1 to 2 is infinity because there is no directed edge, and 2 to 4 there is again no directed edge, which is infinity. And also the previous matrix A1, it was infinity, so we again assign it the value infinity here. Now let's look at this column. 4 to 1 in the matrix A1 was infinity. Now we have to travel 4 to 1 via 2. How do we do that? We travel 4 to 1 via 2. 4 to 1, we go 4 to 2, then 2 to 1. 4 to 2, 4. In this matrix A1, 4 to 2 was 1, plus 2 to 1, 2 to 1 it was 4. So 1 plus 4 is 5, which is lesser than infinity. So in this new matrix A2, we assign 4 to 1 this box as the value 5. Keeping 3 in this matrix A3, we keep the vertex 3 as our intermediate vertex, and we get this corresponding matrix. Now moving on to the final matrix A4, depending on the number of vertices, since our directed graph was based on 4 vertices, we would stop at A4. Now 1 2 3 4, 1 2 3 4, again 4 cross 4 matrix. Keeping in A4, we'll be keeping the vertex 4 as an intermediate vertex. Let's see this column. 3 to 1 was infinity here. Now we have to travel 3 to 1 via 4. How do we do that? 3 to 1 via 4. We go 3 to 4 and then 4 to 1. 3 to 4, 3 to 4 was 2 in this matrix A3. Now we have to go from 4 to 1 because we are finding out this box. 4 to 1 was 5. So 5 plus 2 is 7, which is lesser than infinity. So this box will be assigned the value 7, which is lesser than infinity. Similarly, 3 to 2 was infinity here. Now keeping 4 as our intermediate vertex, we travel from 3 to 2 via 4, which will be 3 to 4. First we will go from 3 to 4. 3 to 4 is 2, and then 4 to 2. 4 to 2 is 1. So 1 plus 2 is 3, which is lesser than infinity. So this new value assigned in the matrix A4 is 3, and hence we get our final matrix as this.